Okay. Intermolecular forces. A really big thing, and they're one of those kind of like basic things that apply to everything. With that being said, this packet is very, very large and covers a lot of different ways that those apply. Okay. Intra and intermolecular forces. Does anybody know what either of those are? Top of their heads.
Forces. Intra is within the molecule, inter is among a bunch of molecules.
Yeah. Intra is within. They are from the like chemical bonds, whereas inter are between different molecules.
Yeah, I like how Ms. Tarleton said bonds. When you break an intermolecular force, you're not necessarily breaking a bond, right? Intermolecular force is an attraction.
So intermolecular forces are also play a role in all of the like physical properties of things. So boiling point, melting point, density, enthalpies, all of that kind of comes from those intermolecular forces because they come from interactions between molecules, as opposed to intra, which is within. Okay, London dispersion and van der Waals. We know that van der Waals is like the umbrella term, hopefully. So London dispersion are kind of nestled within that. So van der Waals.
And we talked about this with Dr. Bonvalet. I'm just going to keep interrupting.
That's fine.
With Dr. Bonvalet, he said van der Waals is kind of like all. It encompasses all intermolecular forces, whereas London dispersion is just one type of intermolecular force.
So London dispersion is a type of intermolecular forces. Do you all know what the other types are? They're also right below. London dispersion, hydrogen bonding, and dipole-dipole. The strongest one is going to be your hydrogen bonding. So you can put that in the strongest force box. Based on our conversation with Bonvalet, you might have to be careful, depending on when the question asks, that you're using the right one, bless you, when you're answering questions, because you didn't get points if you kind of said a different one, so make sure you're really, really clear about which one and why. Between London dispersion and dipole-dipole, which one is the weaker one? London dispersion. London dispersion, and then dipole-dipole is the middle one. Okay. The strength of dispersion forces increases as the size of an atom's electron cloud what? Increases. So if we have a bigger electron cloud, we would have bigger dispersion forces. That makes sense? Then we have polarizability. If you've taken physics, you've all taken some capacity of physics at this point, hopefully, you can think about maybe some.
No, there's people here that definitely not have physics.
Okay. Okay. So polarizability essentially is when you can make a charge happen. In physics, they call it induced charges. It would then be called an induced dipole. So if you had these two things going together, so if you have, essentially what this is showing is it's showing you have your evenly distributed charges. This is the same molecule, but now there's some polar molecules and ions next to it. So what do you think is going to happen over here?
Positive on the left.
Mm-hmm.
Right.
So we have some positive forces over here, negative forces over here. So now we have what's called an induced dipole. So we made the dipole happen by putting those other charges close to it.
My daughter just asked me yesterday about static, because why does her hair get staticky? And I mean, basically, static electricity is just polarizing, right? Just from rubbing your feet on the floor or building up of a charge. So I'm like, how am I going to explain this to her? This is Avi, my 5-year-old. She's like, I'm just like, it's just moving of electrons. She's like, oh, okay. And she was able to move on. So either she really understood it or she didn't care enough to ask me more about it. So, yeah.
So kind of back
basically
to
the same thing, though.
This space here with what is polarizability. It's essentially how easy we can make what's happening in this picture here happen. So how easily an electron cloud can be distorted or be made into that polar molecule.
So is it true that the larger the electron cloud, the more polarizable it is?
Yes. So based on that, maybe see if you can try the next one and put gallium, fluorine, tungsten, which is W, and barium in order from highest to lowest.
This is tricky.
Yeah, that's no.
Yeah, it's no. This one is tricky, by the way. This is more tricky than you'd have on the AP test. There's one here that's going to be like, ooh, you're going to be surprised, I think.
Which one's tungsten again?
W.
W74. So John mentioned that it's going to be based on electron cloud size. Which of those has the smallest electron cloud? Fluorine. So it's going to have the lowest polarizability. Fluorine. Okay. Going from, we're going to go backwards here. Which one do you think is going to be next? What's the next smallest cloud? Gallium. All right. What did you have for this second spot? Why?
Because there's more protons, so it's pulled in more.
I like it. Does that make sense to everyone? Okay, nice.
So just be careful with that because tungsten has more what than barium? It has more electrons, but does it necessarily have a larger electron cloud? No. So watch out for that. Nice work.
That's good. Okay, feel good about the first page? Then flip the page. Oh, they flipped normally this time. Did y'all notice that about, I think it was the first one?
Okay,
Like,
that
looked
was my fault.
backwards? Oh, was it?
Yes.
I didn't know that.
Make fun of me some more.
Okay. We're looking at the two molecules over here on the right. What are the names of these molecules?
CO2, carbon dioxide,
Carbon dioxide. Dioxide. And what's the other one?
Carbon tetrabromide.
Carbon tetrabromide.
So close.
Okay, so we're looking at carbon dioxide and carbon tetrabromide. Which molecule would be more likely to experience an induced dipole? What are you thinking? Why?
Wait, what do you mean by induced?
So on the last page we talked about being able to make that electron cloud or whatever have a charge, and it was easier to do in what situation? With a bigger or smaller electron cloud?
Bigger.
Bigger. Okay, so based on that, which one do you think is going to be easier to induce a dipole in? Tetrabromide. So we've got the CBr4 because the electron cloud is larger.
So is that just good rule of thumb in general?
Mm-hmm. Yeah, the only place where it gets tricky is with the one that we had on the last page where tungsten, even though it would have a larger electron or a larger amount of electrons, because it also has more protons, they're pulled in more. Okay, what about boiling point? John?
I was gonna ask,
Yes, question?
let's say like, I don't know, if it was, obviously carbon tetrabromide is larger,
Mm-hmm.
but if you had like, I don't know, two molecules that were very similar, would there be a definite way of finding out which one had a larger?
No. They're not going to do that to you.
I mean, if you had like carbon tetraiodide, then that would be
I could
more
see
easily
them.
polarizable.
I could see that.
Because those other components would have more. If you had like, what are you thinking? Did you have an example in your brain?
Well, I just feel like, I don't know, something similar, but then similar in like size
Mm-hmm.
of like the different elements, but then
Mhm.
just because of the different elements, they have different bonds, which then makes them.
No.
So if you were thinking about different types of bonds, that's kind of what's happening between these two. Because the carbon oxygen has to be double bond, it's not like carbon tetraoxide. Could maybe be a factor, so making sure you know what kind of bonds are going on and how many things are there and what their electrons look like is going to be the important parts here. Okay, higher boiling point. Guesses? Between these two?
Carbon tetrabromide,
Why?
it's larger,
Okay.
so it has stronger London dispersion forces.
Yes, stronger intermolecular forces. That's what's causing the higher boiling point. So stronger intermolecular forces, higher boiling point.
Yes, so we're getting into intermolecular forces, boiling point, and then what else did we relate to boiling point? Vapor pressure, right? Which vapor pressure is basically just the opposite, right? Sorry, I'm giving it away.
Okay, draw a particle diagram showing how water. What?
Three water molecules. Three
Okay,
water molecules.
Showing how 3 water molecules would orient themselves around a chloride ion. We're gonna start with our chloride ion in the middle.
Ms. Harmon,
Yes.
since both of those compounds are non-polar, that's why they don't have the dipple-dipple.
Correct.
Yes.
Dipple-dipple.
Yes.
That happened.
AKA dipple. Yeah.
Okay, so we know that Cl is a minus because it's a chloride ion. It's chlorine. It's gonna lose, or it's gonna gain that electron, make it a minus. If we think about, I'm just gonna put it over here. If we think about how water looks like this, we have H2O, so our H's are down here, these little ones, and our oxygen is this big one. Where are the charges going to be? Which is oxygen? Is the oxygen going to be a positive or negative? Negative. And our hydrogens are going to be positives then, right? Because we have that dipole happening there. So which way is the water molecule going to orient itself when it's next to the chlorine? Yeah, the hydrogens are going to be towards the chlorine because that's how magnets work. If you think how magnets attract, right, positive and negative goes together, that's kind of what's going on here. So you've got your water.
I think this was an exact question on one of our tests. We drew something like this.
On the AP.
On our test,
Yeah.
we did a question just like this. I think it was 4 though, yeah.
Yeah.
And then you've got your positive charges pointed towards your negative. So on and so forth. And if you went out from here, you could kind of go out and you could figure out what everything else looked like. I drew that really small, I apologize. You could figure out how all of the other water molecules would kind of orient themselves around this based on those charges. Okay. What type of intermolecular force is making this happen?
Hydrogen bonds?
No, it's only with NO.
It's fun.
Okay, so we have an ion and we have a dipole. It's an ion dipole force. That's it.
So the chlorine is the ion, right? It's a literal ion, and then water's a dipole. Hydrogen bonding is a special type of dipole, right? But that's technically an ion dipole force,
So,
which are really easy to identify because it's literally something charged with something that's a dipole.
is this a dipole or ion dipole?
Ion
dipole.
dipole.
Okay. Which one's stronger? Between the two.
Probably, I would think ion, because dipole, you're not going to have a bond. If you had 2 ions, you would have a bond, making me think that would be stronger.
Yeah.
I don't think they're going to ask you. But I think the ion would be stronger because it's not, like, splitting anything. Like, it's just a force. Look it up.
Yeah, I'll check it.
Okay. In this bottom right box, draw 3 water molecules in proper orientation to each other. go ahead and try that.
Ion dipole are stronger than the dipole. Because if you think about it, two dipole is two molecules, right, interacting. But if you have a free agent ion, that's really going to want to connect with something. So the ion dipole would be a little bit stronger than the dipole. Because you got a single ion really wanting to bond with something else. Why is it snowing? You know, because it's like April 18th or something. Because we live in Ohio. Everybody that wants somewhere warm over break is like, oh, I want to go back.
They were complaining about the heat before you walked in.
The heat?
The heat in Florida.
Alan.
I would have loved it.
When was I complaining about the heat?
It was too hot down there.
You literally were just.
I didn't say that.
You were like,
I don't remember.
Oh,
Somebody
because
said.
we were in our uniform.
Oh, yeah, your wolves. That's
It
bad.
wasn't because of like that. Like, if I was in the uniform.
The thing I remember the most about
Ew.
marching in my wolves, when I was at Worcester High School marching in Florida, is we had black shoes on, and it was like a 90-degree day. And I remember my feet feeling like they were literally on fire. It was so hot. That's what I
Okay.
remember about marching.
Did you draw something that looks like this? They look a little bit like Mickey Mouse's. If you haven't noticed that, I've started to notice that. Do you have something that looks kind of like this? You have positives and negatives going to the same direction. That's okay. Did you draw them like that though? Okay, cool. That's what's going on here. If you again were to continue going out, you would have another kind of like oxygen here because it would be attracted to these two hydrogens, so on and so forth. Feel good about hydrogen bonding on this page? Okay, then flip it over.
Wait, so what force is that?
That was hydrogen bonding. All right. In the box to the left, draw 3 methanol molecules. In your drawing, use a dashed line to indicate where hydrogen bonding can occur. Go ahead and try and see if you can find that orientation.
And remember, how do we remember our hydrogen bonding? It's H what? Hydrogen bonding is FON or HNOF. Either one.
It's like a weird mix.
Wow, it is calming down out there.
That was noted.
That would really, really mess us up schedule-wise if we had a day off.
On the weather,
I mean-
it literally says it's raining right now, and it's just not. How is it even snowing? It's
Would anybody even be like really mad though if we had a snow day? I wouldn't.
That'd be through.
Beverly, you would be?
Although I don't know, we have two
I mean, I'd be like mad that we're losing a day of review, but I feel like it's a day off.
We get a day off.
But the other thing is that would get us to 6 days and maybe a makeup day at the end. We don't want that.
I would just skip.
Seniors would have to go one more day.
Can you just skip it if you didn't have anything to do?
Yeah, I mean, it's usually the Monday after
That's good.
prom.
Why did you draw?
okay. Where do you have hydrogen bonding?
Oh, it's not. You don't draw like that.
Between what components? OH?
Yeah.
Okay.
I
Which H do you have it connected to? Do you have it connected to one of these H's or to this H? The H off of the O? Okay, awesome. If you had that, great. These ones aren't going to be attracted in the way of hydrogen bonding, but these ones will. So when you have this, you probably have something OH. This you would have hydrogen bonding with. but you would not have hydrogen bonding between one of the H's off of the carbons and that O. Because of dipole reasons. Feel okay about that? Okay. We have some DNA in the bottom. And we want to know how many hydrogen bonds will be formed between the thymine, which is this piece, and the adenine, and between the guanine and the cytosine. They're kind of set up nicely for you here. How many hydrogen bonds do you see on the top part? Maybe in this area.
Tons.
Between the molecules, so in here. 2. So we have one here and one here happening between, I'll just circle them, that's going to make it easier to see, those components. And then on the bottom, again, they line it up nicely for you here. You have 3. I can't think of a situation where you're going to be asked to do this, like with DNA, but it's good to know where you're going to have hydrogen bonds and where you wouldn't. So between so there's an H here, I promise. You just can't see it, they don't draw it in. There's no hydrogen bond happening here though.
Why?
Because it's connected to a carbon, and it's kind of the same situation we had up here, where only the hydrogen off of the oxygen was going to form that hydrogen bond because of dipole reasons. So if you think about the dipole that's happening here, have you all seen this notation before? Okay, there's a dipole here. This side is the more positive side because oxygen's really electronegative. That's why it's able to do that. That's happening with CH bonds, but not really, which makes that hydrogen less positive and less likely to do dipole bonding type of thing, hydrogen bonding. Okay, we're gonna go to the next page. Feel okay about this?
That's because of the electronegativities, right?
And we're gonna start talking in a minute, soon, very soon, about more application-based things, which might make a little bit more sense. All right, draw a particle diagram of each phase. In a solid situation, we can just do this together, you don't have to do it on your own. What are we thinking is going to happen here? Are they going to be close together or far apart? Close together? Are they going to be pretty ordered or pretty disordered?
Order.
Awesome. So that's a solid. Liquid, are we going to have more or less space in between the molecules?
More.
Okay, are we going to have more or less order?
Less.
Great. Are they going to be far away from each other?
Not too
Really. Because if you think about a liquid in a cup or something, that's very ordered and was not intentionally ordered. They're not, it's not like they're flying away, but they're definitely more spread out. Okay, what about the gas? Ordered or not ordered?
Not ordered.
Close together or far apart?
Yeah.
Great.
Yeah.
That's our gas. Why are solids ordered and close together?
They're packed.
Why? So this whole thing is about intermolecular forces. Do they have strong or weak intermolecular forces?
Strong.
Strong, because they're holding on to each other really hard and they want to be close enough together that they kind of settle into that order. So strong intermolecular forces. And that's why they have that crystalline structure. For the liquid, we're going to have a variety of intermolecular forces. So it could be pretty much any type of intermolecular forces, and they're not held super tightly, and that's what allows a liquid to flow, pretty much. Could be any of them, and they're not close together, or not tightly packed. Do gases have strong intermolecular forces?
No.
Nope. And then we have, they're far away from each other. And it's like a random order. 'Cause they're just trying to figure it out. They're going wherever, there's no order, there's no having to stay in the bottom of the cup, whatever. Random order. Okay. In the beakers to the right, draw a particle diagram depicting the evaporation of 1/3 of a sample of liquid. So we're going to draw a liquid in here.
Oh.
That's our liquid. Did you just draw like a wavy line?
Yeah.
So we're thinking about particles. I have drawn 12 in here. If 1/3 of them are evaporating, how many of them will be gas?
4.
4. What does a gas look like?
Gone.
Gone. I like it. Okay. So there may be out here. Cool. 4 of our particles are out here. What about the rest of them?
Just chilling.
They're chilling.
We keep those at the same.
If this was the AP test, do you know what I would have drawn? Just the
Three-
same time.
3 circles.
I would have drawn 3 in the first, and then 2 on the left and 1 on the yep. That's what I would. But they're never gonna have you pick the number. They're gonna have the number set.
We get 4 times.
Yeah. So you might be you might be given like this first beaker, and you might have to draw or illustrate or write something about the second beaker. Okay. More particulate diagrams. We're gonna draw what's happening in this. C3H8 means we're going to have 3 carbons. We know that it's a gas, but we know that that's a molecule. Since we're only drawing one of them, we don't need to do the notation of like, oh, it's a gas, so they'd be far apart. So we're just gonna draw the one here. That's a C3H8. The big circles are the carbons, the small circles are the hydrogens. So this is our first component. Our O2 is gonna look like that. It's just existing there. We're gonna draw all 5 of them because we should follow the coefficients. CO2, we just had. We know that it exists like this. If you want to do kind of shading to be clear what things are, you can. If we do like this maybe, you can tell what they are. And then for H2O, we know that those are our like Mickey Mouse looking things. And that's what we have going on there. Okay, for this to happen, we know that bonds have to be broken and formed. So I think maybe it's on, let's say that, I put it on the next page? It does, okay. So, for that equation, explain how they must be broken and then reformed to make the products. What bonds have to break? What? What bonds have to break?
C to H
Mm-hmm.
and C to C.
And C to C.
Yeah.
Yeah. We need to break those. We also need to break this double bond happening between the oxygen.
The double bond.
It's a double bond. What bonds have to be formed?
H and O.
HO and CO. Double bonds. This is an important thing to be able to figure out when you're thinking about like entropy, enthalpy, all of those things, figuring out what bonds are being broken and which are being formed to calculate those numbers with that table. So that's what's happening. The if we think about what's happening here, the oxygen are attracting the carbons, the oxygens are also attracting the hydrogens to make those bonds happen. Okay. As the boiling point increases, the vapor pressure, what?
Decreases.
Decreases. Why?
There's less
Surface tension
vapor.
increases.
Because there's less vapor?
Yeah.
What do you mean? Why do we know that, or I guess, in what situation does the boiling point increase? What's happening with the intermolecular forces? They're stronger. So if the intermolecular forces are stronger, are more or less of those molecules just going to kind of be like breaking away to float around loosely? Less, because they want to be held on in the like liquid, say. That's why as our boiling point increases, they're being held down more, our vapor pressure decreases because there's less molecules kind of bouncing back and forth and becoming vapor. So more energy is required to break the intermolecular forces, and that's why our vapor pressure decreases. Okay, we've got 3 sealed flasks, different liquids. Which one has the highest boiling point? Why? Because there's what?
Least gas particles.
Right, which means our vapor pressure is low. I agree with C. The next page is going to ask you to put them in order of decreasing vapor pressure. So take a good look at those flasks. Decreasing vapor pressure. Which one is going to have the most vapor pressure? D, right? Because it's got more of the particles up top. Then what? What's next? A. Okay, then? Yep. And C.
Dab.
That's
Sound
the
like
one. Okay.
Can we go back to that page real quick?
Yeah.
See it sound.
You have a question?
I just had I missed the bottom.
Dab.
Ah, okay.
You just know it as a sound C, and then it's supposed to be. Of course, it's like the pterodactyl.
Okay, so we have what do we have? We have solids, 2 solids. Ammonia has a melting point of 2, and phosphorus trihydrate hydride has a melting point of negative 132.8, both in degrees C. Why are they different?
The name, sorry.
What is
Ammonia
do you know what ammonia is?
It has H bonds.
NH3.
NH3.
Okay.
Hydrogen bonding.
No, she knows.
Yep.
What it was. Like NH3.
NH3. And phosphor trihydrate hydride. We end up with pH3. So we've got those 2.
I think it's pH3.
Is the one with a melting point of 2 or the one with a melting point of negative 132 going to have stronger intermolecular forces?
2.
2. Why does this one have stronger intermolecular forces?
H bond.
Hydrogen.
Is it H bond?
Why
Yeah,
can
H
this
bond.
one hydrogen bond and the other one can't?
Hydrogen's only to NO.
Because it's not pure.
That works. Whatever helps you remember what can have hydrogen bonding works. We can also see, because we know electronegativity trends, hopefully, that nitrogen is more electronegative. You're going to have stronger dipole forces. That's going to cause those H's to be a little bit more positive and cause you to have that bonding. So, ammonia has hydrogen bonding.
Oh, you should tell me.
What forces does phosphorus trihydrate have?
London dispersion forces.
Yeah. Are London dispersion forces stronger or weaker than hydrogen bonding? Weaker.
Well, I guess NH3 has LDS too, right?
Yeah.
Mhm. Okay. Identify the type of each solid described below. Magnesium and iron.
Metallic. Duh.
Metallic
Duh.
solid. Why'd they, oh, all of these say solid. Okay. This is metallic.
Mhm.
What about KCl and ACl?
Ionic.
Mhm.
That's.
Diamond and graphite?
Covalent network.
Mm-hmm.
Wait. Oh.
H2O and SF2? What is that? Silicon dioxide and.
Covalent network again?
Yep.
Joe.
Covalently bonded molecules connected by London dispersion forces, dipole-dipole forces, or hydrogen bonds.
Molecular?
I like molecular. Y'all feel good about molecular?
Yeah.
Solid is composed of a metal and a non-metal in a crystal lattice.
Ionic, right?
Mm-hmm. Do we understand why that's ionic?
Yeah.
Cool. Solid is a great conductor and easily malleable. Mm-hmm. Solid has a low melting point and does not conduct electricity.
No. I think it's molecular.
I like molecular. So we know if it's not conducting electricity, we're probably not going to have a whole lot of charges happening. So it's molecular. And then the molecules in this solid are connected through delocalization of their electrons.
Is that metallic?
That is metallic. Feel good about this page? Okay.
Boom, bada bing.
So for this, we are drawing different types of solids. We kind of already drew a crystalline structure on the other page. We know that that's going to be where they have a structure, they have very much even spacing, they fit into the gaps, whatever that might look like to make that work. So that's your one where they're kind of nestled together. What about an amorphous solid? What are you thinking? Not structured? Okay.
It's not like in a crystal.
Yeah, but it's still a solid, so we still know it's going to be close together. So maybe you get something that's like, I don't even know. Just, you know, not structured. I have a really hard time drawing unstructured things because it just is so much easier to just make them fit nicely. But it's kind of it's not structured. There's no pattern to it. They're just fitting together how they're fitting together. For X-ray diffraction, is a crystalline structure going to have a pattern?
What?
Yes. Why?
What does that mean? Like you shoot an X-ray through it,
Yes, pretty much.
and then like, you
Diffraction.
get a pattern on the wall?
Not on the wall. You would use like a sampling tool. Do you think that the crystalline one is going to have a pattern or not have a pattern?
Like a flashlight.
Actually, you nodded your head. You think a pattern?
What?
Probably.
Yeah, I agree. I think it would have a pattern. Is this solid going to be consistent about what it looks like all the way through?
Yes.
Yeah. Is this one?
No.
No. So this one is going to have clear diffraction patterns.
Oh, like if it was a bunch of sheets.
Yes.
Like if we split like a block into a bunch of sheets, it would have the same pattern between each sheet.
So, X-ray diffraction is a tool that people use to figure out what things are, but they have to be really, really clear and clean. So you can't have like impurities and things. Otherwise, they won't get a clean pattern out. If it's an amorphous solid, you also won't get as clean of a pattern or spectrum or something like that out because it's kind of all over the place. Depending on where you were to look through this, it's gonna look different because of the fact that we have this weird spacing.
Like if
So
you
that's-
have like a bigger strip.
Yeah. So this one is no pattern, pretty much. What about melting points? Are either of these gonna have a sharp melting point?
What does that mean?
A clear melting point. So
That
let's
means just, like,
say,
boom, it melts at this temperature.
yeah, let's
Right,
say we
the
gave
crystalline.
you all samples of the same thing. Are you all going to get the same melting point with one of these? Yeah, which one? I like that. What about if we gave you all samples of this one?
It's gonna be a range.
Yeah, you might get a range. You each might get something different.
Yeah, all this is saying is that a crystalline structure has set properties. Amorphous does not. That's it.
Okay. For each pair, choose the liquid in which the molecules would experience more collisions. Liquid A or B, the one at 20 degrees or the one at 30 degrees? Which one's going to have more collisions? 30 degrees?
Why?
Because
It's going
more
higher.
kinetic energy.
It's going
More kinetic energy. Yep.
Okay, so polar molecules or non-polar molecules?
Hmm.
Polar.
Polar.
Why?
Polar bears.
So like. What?
Okay, but what else is it going to do then?
I mean, it could also like.
And
I like that.
boom.
I like that.
I know
So
what it is.
if we think about like the first couple pages that we did, and you think about where the water is kind of hanging out on that chlorine ion, it's happy there. It's gonna stay there. It's gonna vibrate. We know all molecules vibrate, but it's not gonna go around and collide with something else as much as non-polar molecules are gonna collide because they're floating around. They're doing their own thing. They don't have any issues getting close to other molecules. So for that reason, the non-polar one, so liquid D, is going to have more collisions. What about between E and F? Ones with hydrogen bonds or ones without hydrogen bonds? Why?
Because they can move around. They're gonna move around more.
They're going to move around more, yeah.
Let's go.
We know that liquids can't really like lock into shape like solids can, but depending on what liquid you have and your polarity of molecules or your presence of hydrogen bonds, they're going to move a little bit differently.
I feel like that's a really good AP multiple choice question right there. Because if you think about it, like Ms. Tarpington was talking about this morning, polar molecules are more like a magnet, right? If they hit, a positive and a negative are not going to want to just keep bouncing. They're going to be like, whereas non-polar are going to bounce off. So I thought that was good.
Okay. Solids, liquids, and gases. Yes,
Sorry.
got questions?
So, considering like the liquid stuff,
Mm-hmm.
can we figure out if like comparing two liquids, which one will have a higher viscosity? Because they'll bounce around there, so they'll move more.
You would have to know their vapor pressure or boiling
Yeah.
point or something like that, but not by just looking at it.
Okay. It's hopefully been a long time since you were first introduced to solids, liquids, and gases, and you should hopefully feel pretty good about them. So hopefully this is quick. What are solids gonna look like? A block, okay. Are they ordered or disordered?
Ordered.
Are they close together or far apart?
Close.
This is we kind of already did this.
Okay, liquids, ordered or not ordered? Not ordered? What shape are they?
I don't know.
The shape of the container.
Shape of the container. Okay. Gases, ordered or not ordered?
Unordered.
What are they going to do about spacing?
Fill all of it.
right? So are they gonna be close together or far apart? Far apart. Okay. Which of these three is going to have the weakest IMS?
Yes.
Strongest IMS? What about liquids? Where are they going to be? So they're still weak. The gases are going to be the weakest, but the liquids are still kind of weak. Okay. Solids. What do particles do in solids?
But still.
Not much.
Vibrate.
They vibrate.
Oh.
They move a little bit, not a lot. They only stop moving in what situation? Absolute zero. Very nice. What about liquids? What happens? What do the particles do?
Flow?
They flow. I like flow. They slide around.
So,
Gases? Is there any order happening there?
They glide.
they fly.
Why? Is there any order happening?
No.
They get blown.
Random. They are entirely random. They can go wherever they want.
What?
They glide.
Okay. Feel okay about solids, liquids, and gases? Great.
Like 2 bites of something.
What if we just set these up?
Yeah.
Huh?
If we do them all out, I think we can.
Why would you ask me? That's easy.
I don't even think you need to list it. I would just start with just do the math.
Okay.
As much as I possibly can.
So,
This sounds horrible.
we're going to start with the chlorine question. A sample of chlorine gas, which is Cl2, has the volume of 8.56 liters at a temperature of -11 Celsius and a pressure of 1.25 atmosphere. Calculate the moles present in this sample. What equation do you want to use? Okay. Try it. I'm going to write it up here as you try it, but...
What's 273?
Just say calcium. I think it's 262.
Remember that survey?
Yeah.
Got it.
Just
Nice.
273 minus 11.
What's the
0.082.
you cap it?
I'm not. It's literally 0.08206. It's off there. 0.0206. That's what he's. So,
What R did you use?
Put OA206.
What are the units on that R?
Like lateral column.
Okay. Does it make sense why that's what we use? Because we have liters, atmospheres, we want moles, and hopefully you put your temperature in Kelvin.
Yeah.
So that's the R we want to use. Beverly, did you get a number?
Do you want to put the calculator?
Sure. SIGDIG, we would need 3.
0.49.
So 0.498, is that roughly what you got? Maybe? Is that? I have 0.503. Okay. It probably depends on how far
That's
out you
fine.
went with R, but those are close enough that they would be okay. Within a couple percents. Okay. The next one on this page, suppose we have a sample of carbon dioxide gas with a volume of 5.3 liters at a pressure of 1.72 atmospheres. It's compressed to a different volume of 1.35 liters. What is the final pressure? What equation do you want to use?
And what's the name of that equation?
Kisner.
Let's go. I totally guessed.
Sam Smith got it.
Boil,
Boyle's law.
boil, get W.
I think you're probably more likely to see like the combined gas law instead of Boyle's law. I think you'll see definitely a Pivnert and maybe like a P1 V1 over T1 equals P2 V2 over T2. But just be ready, you could see it.
A good way, if you're not great at remembering the relationships between those, if you can remember Fibner, you can rearrange this, because you know certain things will be held constant. So in this case, you know that NR and T are being held constant, so PV equals PV. Or if you needed T in there, NR are going to be constant, PV over T equals PV over T, so on and so forth. Just put all your constant things, or the things that you aren't given, on one side, and you'll be given the rest of the equation that you need to use. What did you get as a new pressure?
6.75.
You forgot parentheses.
It's just too significant.
Oh, we didn't even put a, this is
Really?
moles. 6.8 what? Elephants?
ATM.
ATM, atmospheres?
ATM.
Is that the number that y'all got?
6.8.
Nice. So we had an amount of gas, we compressed it down to like less than half of its original volume, and our pressure went up. That makes sense? If that doesn't happen, or that doesn't make sense, make sure you think about it that way. Try again, reevaluate, but your pressure should have gone up here. Okay,
They just make them
a sample of diborane gas, a substance that bursts into flames when exposed to air, has a pressure of 345 millimeters mercury at an initial temperature of negative 25 degrees C and a volume of 247 liters. If the conditions are changed so that the temperature is increased to 26 and the pressure is increased to 460 millimeters mercury, what will be the new volume of the sample?
PBT. Oh, PB. PBT. PBT.
P squared, U1 V1 squared, times V.
Wait,
You gotta do
It's
like
just P1, D1,
E
T1.
squared.
Good for you.
Plus the square root of 7.
I don't think they put their work for this.
Which one are you doing?
I mean, it's just gonna be
Right, so I was gonna convert
Yeah.
that to.
Oh, shit. Speed.
You have a pressure, temperature, volume.
I'm just
That's the combined gas law.
Yeah, what?
So it's 0.00345.
What?
No, I think it is in millimeters, isn't it?
You could.
Millimeters?
There's no reason you couldn't leave that in millimeters of mercury, but you do have to change your Celsius to Kelvin because you can't have a negative number. That's gonna mess you up.
What about what is it normally though?
What?
From mercury to
760 millimeters of mercury in 1 ATM. Also 760 millimeters of mercury is 760 torr, which is also 1 ATM. Torr just renamed it to himself because why wouldn't you?
Calculator?
I don't know.
Okay, what did y'all get for volume?
2.2.
2.2.
2.2.
2.2.
2.2 liters.
2.2 liters. Okay. So we're increasing pressure and we're increasing temperature. So that makes sense that our volume changes a little bit, but not a whole lot. Okay, sum of the mole fractions of all the components present of something are going to be equal to what? Kind of taking a turn here. To 1. Right? Because we want to know how much we have in our holes. A hole is 1, so we need to make sure that if we have a couple of parts, we add up to 1.
That's good.
So that leads you into the next question. The partial pressure of any gas in a mixture is the total pressure multiplied by the mole fraction of that gas. This conclusion is a direct result of the ideal gas law, which assumes that all gas particles behave ideally. So we know that the tank contains 370 grams of oxygen and 67 grams of helium, the total pressure of 7 atmospheres. Calculate the following. How many moles of helium are in the tank? What do you want to start with?
What the helium gas is it H or H2?
Helium is He.
It's a noble gas.
Convert to moles. Okay, so we have 67.0 grams times 1 mole per 4.003 grams of helium. You end up with 16.74 moles of helium. Okay.
But that is just HE, right?
Mm-hmm.
Yes, John.
Nice
Like
work.
in the gas form. Okay.
Yes.
Talk to me when
yes.
we do oxygen.
So, how many moles of oxygen? Same deal. We're going to start with our 370.0 grams times 1 mole over 32.00 grams, and you end up with 11.56 moles of oxygen, which is
Yeah.
O2.
See?
Yeah, but you were totally
O2.
right.
I thought it said H. I thought it said hydrogen.
What is the total number of moles of gas in the tank? 2.
27? 28?
28. 28 point.
3.
0.3 moles.
Let's go draw.
That's just addition. We're just going to add these two numbers together. That's our total moles of gas in the tank. Now we want the mole fraction. So we want to know how much of that whole tank is helium. What are you going to do? What are you going to set up?
It's just percent
Divide.
composition, right? Yeah.
So moles of helium over total moles. I think this one comes out as about 0.592-ish.
Yep.
This one comes out as 0.405. Oh, 409-ish. Which also, if you wanted percents, you can make those percents, so like 59% helium, 41-ish% oxygen. Partial pressures. We know the total pressure, so you can figure out the partial pressures. You remember how to calculate partial pressures?
Negative.
What is he
So-
about?
Partial pressures, pressure 1 plus pressure 2 plus pressure 3 equals everything. You just add them together.
So if we know that our pressures that we're going to get need to add up to our total pressure,
7.
yes, they're going to add up to 7. How do you figure out the partial pressures?
Did you do the mole fraction?
Mm-hmm. So 7. Is that? Oh, sorry. Yes, there's that.
Zoom out a tiny bit too.
Okay, so to find our partial pressure of oxygen, we're going to take the total pressure, we're going to multiply times the mole fraction, and then you'll get a number in atmosphere here because this is in atmospheres and this is a fraction, and I think you'll get a partial pressure of about 2.86. You're going to do the same thing for the partial pressure of helium, 7.00, this is atmospheres, times your mole fraction is 0.592, and you should get approximately 4.14 atmospheres.
So if you converted D and E just to percent, you can just take that percent of 7 then.
I mean, that's what we did.
Mm-hmm.
Yep, that works. 0.86. Feel okay about this math? I'll leave it up here for a second.
He's quiet.
So we know because the helium made up more of that total, it also was going to take up that much of the pressures. You add these together, you'll get 7.
Good stuff.
All right. Next page.
You know why that would happen?
In a tank,
Because of Newton's law.
27 liters of helium at 25 degrees C and 101.3 kilopascals and 12 liters of oxygen at 25 degrees C and 101.3 kilopascals are pumped into a tank with a volume of 8 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees C. Kilopascals. It's pressure. Where do you want to start? What are you thinking that you might want to start with? Okay. We don't have a couple of those pieces, but we can do what I was talking about before. We need to come up with something that kind of relates to the information that we have. Do we have an N?
No.
Do we have an R?
Yeah.
Yeah.
We know how many moles of gas we have?
What's that?
Not really. Oh, that is N. Sorry. We don't know N. We have an R, but not really. We don't really have an R that relates these things. And if we did, it's going to be the same. It's going to be the same, but we don't have one in kilopascals. It's going to be the same. Do we have a T?
Isn't,
Do we have a temperature?
there's one ATM though.
We kind of have a temperature, but it's gonna stay consistent. So we don't need to take that into account. So we're actually gonna do what we did before, and we're gonna use P1 V1 equals P2 V2. So that's the information that we have, and that's what we can relate. You can use that to figure out your pressure of your two components. So we're gonna start with one of them. Let's start, say, with the helium. So our P1 is 101.3 kilopascals, and our volume 1 is 27 liters. And that's going to be equal to our new volume, which is 8 liters, times our P2. We don't have a P2, but we would like a P2. We want to know the pressure of the helium inside that container. If you do this math through, you get a P2, which is your helium pressure, of 341.9 kilopascals. You can do the same thing for oxygen. P1V1 equals P2V2, where again we have 101.3. And for this one, our initial volume is 12. And then we have our final volume of 8 again, times our P2. So your P2 of oxygen is 151.95. And those are your partial pressures of each of your gas at 25 degrees C.
No, we could just add those for the total pressure.
Mm-hmm.
So what did you do for the second P2V2?
For what?
The second P1V1 equals P2V2.
Okay, what about it? This is all the oxygen. So we started at 101.3 kilopascals and 12 liters,
Yeah.
and we ended at 8 liters. And so then we can find the final pressure. Because we know that those two gases are doing their own thing, and that's why you can find their partial pressures. Questions about this one?
Is that 15 point?
151.95. 151.95 kilopascals. All right, we are drawing graphs to compare pressure and temperature, volume and temperature, and pressure and volume. As pressure goes up, temperature what? As volume goes up, temperature, as temperature goes up, volume does what? Up. because we know in this one, we have to keep the pressure constant. So if we're increasing the temperature to keep the pressure constant, our volume has to increase. What about this one? As volume goes up, what happens to pressure?
Wait,
Decreases.
volume increases, doesn't
It's
pressure
inverse
decrease?
relationship.
Yeah.
So then wouldn't that make the first two graphs not be the same?
So for this one, we're holding pressure constant, and for this one, we're holding volume constant, and that's why we have to have that relationship. Okay, so this one, they have it drawn like that. You could also, if you want to, do that.
Why is it a curve though?
Because that's how it works.
Because that's how they were
That's a
saying.
different relationship. That's like, there's a linear, like, there's a negative linear relationship, and then there's a negative square root
So-
relationship.
If you want to just draw it as a straight line, you can. This is what the relationship looks like.
But why is it a curve?
It's an inverse relationship. It's a hyperbola. Hyperbola. That's how it looks.
So these two, one increases, the other increases.
You don't want a
are
negative
direct.
slope.
And then our last one, as Mr. Heller just said, is inverse.
Oh, right. I messed it up.
It's just how it is.
Yeah, thanks, Alan. I'm gonna get through the world just being how it is.
Okay. Our constants in all of them, they all have moles constant. What else does the P versus T relationship have constant?
Volume?
Volume? What about the volume versus temperature one? And the pressure versus volume one? Temperature. I know it seems basic. These are going to be the important things when you're thinking about this, when you're thinking about the thou shall not forget. These relationships are important to know.
5-minute break.
5-minute break?
You said that I shall not forget is gonna be on Thursday.
When?
Left.
It's Tuesday.
No, but I thought you said it's gonna be on Thursday. Left break.
Okay.
I can get a minus.
So, kinetic molecular theory is our next one. We have hopefully seen these graphs before. Hopefully
Maxwell
a lot.
Boltzmann.
Let's go.
These are actually good questions. I don't know. Raising the roof.
Okay, so we have two samples of gas. One of them is at 72 degrees C, and the other one is at 37 degrees C. Which one has more kinetic energy? A. Why?
Higher.
Higher speed, I'm sure.
Higher temp. Great. Okay. The diagram to the right shows a distribution of speeds for a sample of H2 at 25 degrees C. What would it look like if it were at 55 degrees C?
But the peak would be further away.
The peak would be further away.
Yep.
Okay. So we're thinking maybe something that looks like that. Hopefully that was
It also
clear to your
needs
mind.
it also needs to be lower, right?
Yeah.
Oh, shoot.
Wait, why wouldn't the molecules be the same?
They are the same.
Just spread out.
They're just spread out over a larger area.
Okay.
Those should be shorter than the, are they supposed to be the same height?
No, they should be at a lower height.
Yeah, no, that's a different.
Because you're spreading out more molecules. Think about that activation energy. You have more molecules at a higher energy.
It might be more spread out, but in the sample, it's not like the molecules decrease.
It's not. It's the same amount of molecules, just they're spreading out over a larger area.
So because a higher percent of them are moving at a faster speed because of the higher temperature, it gets moved, our peak gets moved, all of that. There's more kinetic energy. Feel okay about this one? Yeah. Okay. This diagram shows the distribution of speeds for a sample of H2 at 25 degrees C. Again, add a line that shows relative distribution of speeds for a sample of
That's just supposed to be
fluorine at 25 degrees C.
F2, not FL2. Now this is a good question. Think about this.
What is that though?
It's nothing. It's fluorine.
So fluorine, we have fluorine, we're comparing it to hydrogen gas. They're both at the same temperature.
So what's the difference?
What's our distribution going to be?
The speed is lower.
Bigger because
The mass of the particles.
So what does that mean for our peak?
It's more to the left.
Yep.
Okay.
And it's
becomes the
higher.
peak.
So we're looking at maybe something like that. Feel okay about that? It'll kind of go like that. Okay. We know that because fluorine has a higher molar mass, and so it's more of its molecules are going to have a lower speed because they're heavier, they're bigger. Feel good about that. Okay, flip page. When using the ideal gas law, what is assumed about the gas that makes it ideal?
1 ATM.
High temperature.
Okay, I like small, volume is negligible.
No interaction between molecules.
No attraction between molecules. Negligible. And no interactions or intermolecular forces. Okay, analyze the particle diagram of A and B over here. Both gases have the same volume and are at the same temperature. Which sample would deviate most from the ideal gas law? A, why?
They're too big.
A, volume isn't negligible here because they're of their size, they're larger. Volume isn't. Okay,
You're negligible.
Oh,
you are
You got it.
you are observing the behavior of two gases, a sample of H2 and a sample of NH3. Which one would deviate most from the ideal gas law? Why?
It's less than
It's larger and it's got hydrogen bonds.
You guys remember doing this? This is the
Well, the NH3 is 8 times as big.
this is the deviation from the ideal gas law. Remember doing this, Pogel? Yep.
The
we
hydrogen bonding is going to be the big piece here. There's going to be hydrogen bonding. That's going to affect it more than the volume is, but it's going to have way more intermolecular forces. So our intermolecular forces can't be negligible. Okay, you're observing a sample of gas at a very low temperature. The pressure would be higher or lower than the ideal gas law would predict at a very low temperature. Lower? Why?
Because pressure and temperature have a direct relationship.
Okay, so as pressure goes down, temperature goes down. What do we know kind of goes along with temperature? Kinetic energy? Kinetic energy. So the molecules are slowing down, less kinetic energy, less likely to interact with each other.
Would it?
Question?
I feel like it would still be higher though.
Why?
Like the only time that I don't know. I feel like at absolute zero you would have basically an ideal gas, right?
Absolutely.
Because
The ideal gas law is assuming that the gases are moving, they're just not interacting.
right. So
At
they-
absolute zero, you wouldn't even have a gas. You would have a solid.
Ooh.
But they're still like interacting though. It's not
They're
at the
inter-
absolute zero.
But they're interacting less than we would expect a gas to be interacting because it's at kind of a crazy condition. That's what's going on here.
Sure.
Okay, under which of the following circumstances would a gas most closely follow the ideal gas law? So,
Wait, I got this. We got this. Don't
okay, make your prediction. Is this saying it's a switch? Okay.
wait, what's the ideal gas?
What are we thinking?
6 ATM 100K.
6 ATM, 100K. This is what we have one guess for this. No,
I would
not this one.
No.
Okay. Which one do you think it might be?
The one above it.
The one above it.
This one?
Yeah.
Feel good about this one? Why?
Well, they're on opposite sides, so one split in half.
Low pressure, high temperature.
So we know at low pressures, things are going to be really spread out. The volume of those gases, of those particles, is negligible. And at high temperatures, there's less opportunity for intermolecular forces to act because they're doing their own thing. They're zooming around. They're acting pretty much how we would expect a gas to act. Feel okay about that? We kind of have talked about all of those components up here, so I'm not going to write it again. Okay.
You understand that.
This page
Understand that.
is homework. Go ahead.
We don't have
and
time.
star this page.
Is it just
Lots
one
of
page?
stars, something like
What
that.
did we do?
Maybe fold.
I told her to do it, so you can yell at me.
Fold this whole corner down because both sides of this page are homework.
That's just math.
It's so
I already
maybe-
have, man.
because it's a really big packet. Just like maybe fold the corners so you remember that's the page you have to do. Both sides of the page. So your first page is you're calculating masses, calculating concentrations, piece of cake. Second page, you're drawing particulate diagrams. I think you'd rather draw particulate diagrams on your own time anyway.
The thing is that you don't have to do it. I mean, it's really your review. So tomorrow we'll go over it very quickly, but if you haven't done it, it's not going to mean much to you. So do it.
Okay,
It's your review. So
so we're on this page now with this cylinder looking thing over here. You were curious about the different dyes that make up the ink of a black dry erase marker. Use paper chromatography to figure it out. What is that going to look like? Do y'all remember doing this?
Paper strip.
What did it look like? Paper strip?
Paper strip.
Pull that thing go up. If it's in water.
And it's in a liquid.
Ooh, I like that.
Oh, yeah.
Above the liquid, we have our line and we have our dry erase marker. That's what we're testing on that line. So that capillary action, the liquid gets pulled up, it goes through the marker, it drags those inks up. Okay, you find there are dyes in your dry erase marker. We know the RF values, so you can figure out where they go. So this is our sample, and we know we have the yellow dye has an RF value of 0.25, so if it say gets all the way up to here, our solvent line is up here. About a quarter of the way up, that's going to be our yellow. About halfway up is our purple. And 3/4 of the way up, we have some black dye.
Was that what RF is? Just like how far the solvent line goes?
Essentially, because it's the distance that you are out of your total. So 75 or 0.75 is 75% of the way up.
Wait, what's that word after solvent?
Line.
How far the solvent went up. Remember how we did this and they never actually separated?
Yeah.
This is your solvent line. You can
It's
do it with
what-
chalk too, I think.
What?
You can do it with chalk too.
Maybe we'll try that after the AP test.
Yeah, that'd be fun.
Okay.
We could also do it with chlorophyll.
Okay.
Okay, so RF value, we kind of just talked about it, is equal to, they have A over B, where let's say we were calculating the yellow dye, this distance is A, and this distance is B.
Oh.
Alright, out of the three, which dye is most likely the most polar molecule?
Black.
Why?
Friends.
Okay. Which means it was more or less attracted to the solvent. More. And our solvent in this case was water. If you take chemistry in college, you might use polar and non-polar solvents. It's way more complicated. We're using water. It's polar. Polar molecules are going to be pulled up with it.
Wait, I have a question.
Mm-hmm.
I think I talked to Mr. Hell about this like briefly, but would non-polar substances go up the paper?
Yes.
Just not as far.
Only a little bit though. Yeah.
Okay.
But you could make like a mix of polar and non-polar stuff, and then it would move more, or some things would move less. It gets really complicated when you get to that point. But for this sake, we're using water. Polar stuff is going to move. Non-polar stuff is not going to move as much. Okay. Instead of paper chromatography, your partner chooses to separate the same dry erase ink using thin layer chromatography. Uses a glass slide covered with silica gel and a solution that is much less polar. When finished, what is the most likely order of dyes from top to bottom?
Yellow, purple, black,
Yellow, purple, black. Why?
because they're opposite player.
I like it. So you're using a less polar thing, so the less polar things are going to get pulled up further.
Got it.
So we get yellow, purple, black. Feel good about chromatography? They're going to switch because we're not using something polar, so the things that we know aren't polar, which we know from the first time, are going to move further.
That's one of the three main ways to separate something, right? Filtration, distillation, and chromatography.
Okay, the lab group across the room uses the same dry erase marker but separates the inks using column chromatography. Don't do any column chromatography. The column contains silica gel and they use a solution that is much less polar. When finished, what is the most likely order of the dyes from top to bottom? So column chromatography, you take the stuff that would be on on like the silica gel, you put it in a tube, a burette looking thing, and then you run your liquid through the top. And so it kind of travels in the opposite direction. So the things, let's say you were using a polar solvent, the polar things are going to get pulled further down the column. The less polar things are not going to get pulled down as far. So based on that, if we're using a non-polar solution, from top to bottom, the top is your starting place. What is the order of your dyes? Why?
Because it's the opposite order of like the top to bottom thing.
But we have a
It's also
non-polar
non-polar.
solvent.
Yeah, it's the
So
Yeah,
which
so
one's going to
it's-
go the furthest?
So black purple, yeah.
It's the opposite of the water, right?
Are you sure?
So
Yeah,
it's
or-
gonna
That's gonna pull down.
it's gonna pull the least polar thing the furthest. In our experience, we figured out, right? It's okay.
Black is polar, so it's gonna be the top.
Oh, okay. Yes, yes.
Going from top
Yellow,
to
purple,
bottom.
black. Yellow would move the most, but it would be at the bottom
Okay.
because
Right.
it moves this way.
Okay.
So from top to bottom, black, purple, yellow.
Yes.
Boom.
Well, we're using a non-polar
Nice
substance
try.
from the top to
Are
the
you
bottom.
trying to?
So
As the water.
it's the same as the
Yeah.
water, but
Yeah.
it's not for the same reasons.
Yeah.
Okay.
I mean, it's the same science, but when you switch, if you switch to the non-polar and it's also going down, that's why it's the same order.
It's reversed.
Yeah.
Okay. Do y'all recognize this setup?
So they did that in CP Chem.
Okay.
No, we didn't.
You should have separated the cherry Coke in CP Chem and Salvaggi. So some of you did not, but that's what you should have done in CP Chem. It's a distillation apparatus.
I couldn't.
So this is used for distillation. For this, you can kind of see what's happening down here. You have something on a hot plate. You're boiling things. And then some of those things, if they're getting up pretty much high enough, quick enough, would come over into this other side.
And in that tube, that glass tube in the middle, there's cold water running through that. So you're evaporating a gas, and then the cold water causes it to condense, and that's how you separate it. That's a distillation.
So
You would have done that in CP Chem last year if you had it in person.
this is happening because of differences in boiling point. So because some things are boiling and some things aren't, the things that are boiling are the things that you're collecting, which is a really convenient way to do things because normally you like boil something off and that's not the thing that you collect. In this way, the thing that you're boiling off is the thing that you collect. How does filtration differ from distillation?
Filtration is based on physical status.
Well, filtration is based on particle size,
That too.
not the boiling.
What does physical status mean? Like,
So the difference here is filtration is based on size. We already know that distillation is based on boiling point. So kind of with that, you could filter this. The example of this has is you could filter sand out of salt water, but you couldn't distill sand out of salt water. You could distill to separate the salt from the water, but that's kind of an example of where they're different. So it depends on what you're trying to do, depends on what you're trying to collect. All right, you have a solution containing 50% liquid A and 50% liquid B. Liquid A has a boiling point of approximately 70 degrees C, while liquid B has a boiling point of 100 degrees. You want to separate them by distillation. At what temperature would you expect the solution to begin boiling?
85.
Why?
Because it's right in the middle and they have the same percent volume.
I like it.
What?
I like to.
Oh, they're mixed.
Yeah.
So that's
Swish them
when
around.
the solution would begin boiling. Why must you continue to increase the temperature as you perform distillation?
Because it slowly gets closer to 100 degrees as you get rid of liquid A.
The boiling point? Yeah. So as you boil off the thing with the lower boiling point, your mix becomes more of the thing with the higher boiling point, which raises your overall boiling point. So you need to keep going up. If you just went and you sat it at 70 degrees, you're not going to get everything out. You're not really going to get anything out. So this is because of the ratios, essentially, if that makes sense.
Ratio.
You create the distillation curve on the right. Label on the location.
So
Okay.
we'll pause there.